the record is now on. So let's say I think to focus on the trust for the virtual work is like a good introduction, because you can see that each work very clearly. So the internal work is, I can say, discrete, because a trust is a system of members put together. But when we start looking at the beam now, okay, the external part is simple enough, because you see that you just apply the load again where you want to know the displacement. And when your beam deflects down, this virtual load is going to travel with your beam. So the external load part is well taken care of. But when it comes down to the internal work, how are we going to take care of this? Because first and foremost, you can sort of look at the force, the tiny little force in your flexural member by, looking at the small area multiplied by the stress, right? Like stress multiplied by dA, and dA is B dy. But a little problem with this is that stress in your flexural member is not constant. So we are talking about the stress that keeps varying throughout the cross section. So in order to get the internal response multiplied by the internal displacement, you need to calculate the displacement in each area of your beam multiplied by the internal response. And it involves a force which involves a stress which is not constant. So integration is required. I don't want to dig into this very deep, but you can see that's the internal response is stress multiplied by the area, which is the force, right? Stress is my over I, if you can recall. Did you recall bending stress? It's my over I, right? Multiplied by the area, the small area, which is B dy, the strip. And internal displacement is just the strain here, okay, which is equal to epsilon applied by dx. That's strain at any location due to the actual force. So strain here is stress divided by the Young's modulus. So it's my over I, but this is big M, not the truck, but big M here is the actual, right? Small m here is the virtual. So you put them in the equation to get the internal work. One is the internal response due to the virtual load. It's stress multiplied by dA, which is the force. Another is the displacement due to the actual load. So it's again stress divided by Young's modulus multiplied by dx. Now you have dA multiplied by dx. So that means triple integration. Three of them. You like it so much, you can't have one, you have to have three, right? So dA dx, we can wrap this up. The y squared dA, that's the moment of inertia, right? So from here, it all comes down to just one form, because the y squared dA is gone and it's moment of inertia. So instead of having I squared down there, you have just one I. So this is not straightforward as in the trust, because in the trust you can say it's discrete. Discrete, it means that you can count it one member by one member in the system. But in the beam, it's a stress in the section, so it becomes like a continuous problem. Can you recall your statistics? You guys took statistics already, right? Yeah. So in statistics, there are the discrete one and the continuous one. So it's the same thing here. So when you have the continuous one, whenever you see the word continuous, that spells integration. And the Bernoulli equation for normal distribution in probability is one equation that changed the world. Without probability, our world cannot exist. So I try to appreciate that, because in the real world, if I ask you how much force here do we have to design the floor, your correct answer would be, how the hell would I know? Right? And again, if I ask you, what is this concrete strength that we use to build the column? Again, your answer would be, how the hell would I know? Right? That's why we study probability. So we could make what we can use the pretty words to call it educated guess. We can guess with proper education. Okay, the strength should be around this, that. So okay, we can do that. We can do everything because of probability. That's the thing. Okay. All right. So here we are. Because this is continuous problem. So the equation that you see here is not really going to demonstrate the fact that this part is virtual or that part is actual. But the big M is the moment equation corresponding to the actual work case, actual load case, sorry. And the small m is the moment equation corresponding to the virtual load case. So yeah, that is your beloved equation now. There. But I believe that you guys have got that, right? You guys will report. Look at me. I'm not a guy to report now. Okay. Here. One thing that you can tell is, oh, it's a little bit here that this box it. In case of deflection, we apply unit force. In case of rotation, we apply unit moment. Keep that in mind. And when you have this, you need to be able to do two things. If you ask me, in some way. First, of course, you need to be able to write moment equation. Correct? That's a gimmick, right? Because we need an equation here. So first, you need to be able to write moment equation. Second, because we multiply them, that means in order to multiply two functions, you need to have two functions on the same domain. Does that ring a bell? Which means, in fact, if you are going to write the big M equation as a function of x and the small m as a function of x, they must share the same range. For example, if the big M equation is applicable from x equal to 0 to x equal to 5, your small m should be of the same range. That is from x equal to 0 to x equal to 5, not x equal to 3 or 2. Can't multiply the two functions that have different domains. Okay? That's it. So, without further ado, just go back here and try to solve the deflection. Use the virtual to derive the basics. Wow, the maximum deflection not being shown. Can I do this? Can I? You think so? I like to think so, but I'm not so sure. So let's try, okay? They usually have the some kind of tool that I can rest my microphone on, and that is gone. I probably need to have adjustment. You see, in order for this not to fall, for the microphone not to fall down, what do I need to do to make it stable? Let me ask. Simple equilibrium. How do I create equilibrium for my microphone? Simple. I need to try to place the center of gravity on the folder, right? If I place the center of gravity of the microphone on this, now I know, okay, the center of gravity is probably here. Voila! And open a little bit closer to my mouth, so it's like playing concert. Okay, here we go. And you guys at home, can you still hear me? Okay, so this experiment works, right? Anyway, so again, it's just because we're talking about the virtual work. So if I'm going to derive the basic formulas for maximum deflections of the beam shield, I need to know where the maximum deflection is. In the first case, this is my actual load. And so I know, of course, the maximum deflection should be here, right? Can't be here. Here. So I know this is where I need to apply my unit. Okay. And there is my actual. This is my virtual. So, okay. Right. Let's take care of the actual load case. I don't know what I should do. Maybe I should write more because if I go too quickly and you don't see a lot like this, you're gonna have a structure. So the easiest way to write the moment equation in this case would be to start from the free end because everything is zero, right? So I will start my x from the free end, going from right to left. And in order to do that, if you're not very comfortable enough, you will probably need to cut the free body diagram and take the moment here. Yeah, that's how you get your moment equation. But for me, sometimes it's just, because I've done this so many years, so it comes very naturally to me. The load is W, correct? So the total load between this area is Wx. Taking the moment arc is the x over 2. So the small moment here is simply the negative moment, if you want, minus Wx squared over 2. And the range here would be from 0 to L. Oh, that's a block. Okay, so any questions about the virtual load case? So again, if you ask me, the skill to write the equation is like high school math, right? But this is coupled with a little bit of engineering knowledge. So you write the moment equation. It's still up to this point, it should be physical. Now, I move my virtual load case here. Wow, can you believe that? The lengths are equal. Woo! Excellent drawing, right? So anyway, I'm sorry, this the actual load case, so this one should be the big M, right? The next one, this is virtual load case, so we should use the smaller. And again, if you're not very efficient, this you're gonna have to cut the free body diagram, and okay, I'm gonna take moment at this point, and that is x. So my moment is now minus 1x. With a similar range. Now we have to click there. All right. Account for the we need to account for the whole work. So that means we need to perform the integration throughout the length of the V. So that max becomes integral from 0 to L of right, minus wx squared over 2 multiplied by minus x dx over dr. And you could have a lot more difficult integral to go through, but consider yourself lucky that we don't study electrical engineering because they would do the Fourier thing. We don't, right? Fourier, it's a Fourier, right? Fourier. Or we don't do things with imaginary number. I remember I began to struggle because for the love of whatever you love, what is that? Can this be true? It's not physically impossible, right? But they say because they could not take the square root of minus 1, so just I, it's called I, U, B, V, A, so we can carry on. And once they started calling this, they could create electricity for us. Without this, we don't have electricity. About that. Without Fourier, we don't have mobile phones. About that. These guys just, I don't know if I should praise them or curse them. But anyway. So, yeah, this integral, what I'm trying to say, that you should be able to do it. Right? Piece of cake. If you don't want to do this, go do Fourier series instead. This is we are dealing with maybe one of the easiest mathematics you could have for university level. Okay, so let's look. Minus minus, so it's gone. Wx cubed over 2ei dx, which is it's wx to the power of 4 over 4 multiplied by 2, so 8ei 0 to L, which is WL to the power of 4 over 8. Very easy, Wow. Did it match what we did in last week? Of course it did. Just. If you don't believe me, you can try to scroll back, see if I got this number when I use the moment area method. You do believe me, right? Because you're too lazy to go back. Go back, see. Yeah, of course. It has to. That's some kind of protest. Okay, so let's try the next one, shall we? That's your actual. Sorry, you're writing something down, maybe. Okay. Too small. Allah. Too small. Okay. Now let's try another one. That actual. Oops. Now actual becomes big. Actual. Where is the maximum deflection of this beam? It has to be a midspan, right? Because it's symmetric. So we are going to apply the unit load somewhere. So let us begin on the next page. Ooh. That's actual. And then we know the virtual, it has to be a midspan. So okay, this one is a little bit more, work, because now when you look at the actual, we need to do a little analysis, right? And now we know the reaction here is equal to WL over U. And when you cut the free body diagram here at any X location, let's say if I begin from X here, there will be two terms involved in the book. Before we start off, let's try to take a look at the say our problem as a whole. This is the virtual case. That is the unit load. If you look at this beam, you know your bending moment diagram looks like what? Your moment diagram looks like this, right? Am I right? Come on. Point load, bending moment diagram. 2 seconds. Not enough friction. 2 seconds. Just to draw what you have already in your mind. Right? And point load in the middle, the moment here is PL over 4, right? You should know that P is 1, L is L over 4. All the time. It comes from the fact that this is 1, which is P over 2 multiplied by L over 2. See? It's PL over 4. Even if you dream about it, you have to dream correctly. Simple stuff. And here is a half. So what does this bending, the quick bending moment diagram tell you? It tells you that you must have two equations to explain the moment in this case, because this is one equation. That's another. You can't have one equation. See? But for the virtual case, your bending moment diagram is like that. It's one curve, so it's one equation. So when you see the situation, you need to start planning on how you are going to write your moment equation. Right? So here, actual case, it's one equation, but virtual is two. But again, because we have a symmetric structure on the virtual case, which means this equation and that equation is the same. It can be the same if you start one x from here and another x from there. Essentially, it's the same equation. Correct? So the point is, because of the discontinuity of bending moment diagram in the virtual case, you need to split your integral. But because they are similar, because of symmetry, it means that I can do one integral and multiply by 2. but I need to split the integral because of the discontinuity here. You see that? So let's see. Actual case, moment equation will be WL over 2. That is the reaction, right? For those of you who cannot see this, draw the free body diagram. This is the reaction. So it is multiplied by X, goes up. So it creates positive moment, right? And the uniform load comes down, so it creates negative moment. And the load coming in, the moment coming in from this load is essentially a negative moment, right? So it's WX multiplied by X over 2 if you take the moment at this location. So it's WX squared over 2. If you cannot see this, you need to draw the free body diagram right there. But you know, I can see it, but I don't have to. But if you really have to, this should be your free body diagram. X WL over 2. That's W. Okay, and you take the moment at this location. So, you need to do things like this very efficiently now, because you're supposed to be able to do it sin statics. You're not supposed to, revisit this again and again and again in the future. We need this. We need to move on from our basics that you're supposed to take care of long time. And the range, because we now know we need to break the integral in the virtual case. So let's say it's from 0 to L over 2. Now we can write the moment for the virtual case with ease, because now we know that the range is the same. So again, we cut the free body diagram here. It's the last time I cut the free body diagram. This, but I tell you to draw the free body diagram, right? If you can't see the picture, you must draw the free body diagram. If you can see the picture, you don't have to draw it. Nobody's gonna say anything bad about you. But if you can't, you better draw it. If you can't and you don't draw it, it means you cannot draw the free body diagram. This is a half, so take the moment at this location. Your moment is, of course, X over 2. A half multiplied by X. Okay? Same range. Questions, maybe? Again, the question should be, well, you think this is difficult? Come on, man. I'm bored. Too easy. So the deflection max here should be, I'm not going to use, okay, one more time, maybe, why not? Integral of this WL over 2x minus WX squared over 2 multiplied by X over 2 dx over EI. But remember that we need to split the moment equation in the virtual case. So this integral is from 0 to L over 2. And because of the symmetry, we take advantage of that. So we multiply this integral by 2 to sum up the entire work of the system. Right? Looks like we can do some dirty work like this. Yeah. So now, there are folks who are so cool and they become careless. But if everything integral at once, then they make mistakes. Silly mistakes. Just sad. We can just go step by step. Oh, so multiply it out. WL x squared over 2 minus WX cubed over 2. Am I correct? Hope so. Dx over dr. Now we're going to perform our little integration. This is WL cubed over 6ei from 0 to L over 2 minus W x to the power of 4 over 8, right? Again, from 0 to L over 2. Now you're going to have to help me. I'm old. Right? I can make easily some easy mistakes here as well. So, okay. Because the second term is 0, so it should be easy enough. This becomes WL to the power of 4, but you have 2 to the power of 3, that's 8. 8 multiplied by 6, so that's 48, right? Am I correct? Or are you waiting for me to make a mistake? Maybe? Minus, okay, that's a WL to the power of 4, and 2 to the power of 4 is we have 2 to the power of 4, and 8 is 2 to the power of 3, so that's 2 to the power of 7, which is 128, right? You know, I used to teach mathematics to my daughter. She doesn't seem to like it at all. I get frustrated after like 5 seconds because I couldn't understand. Why couldn't you do this? You know, this is when you use the least common number. That's 2 multiplied up. Sorry, that's 3 multiplied by 2 to the power of 4, right? Yeah, that's 2 power of 7. We can use the least common number. Get that? So it is 2 to the power of 7 multiplied by 3, right? That's your denominator. Oops. Yeah. And so this is 8, right? You're missing 2 to the power 3 here. You miss 3 minus 3. That's your displacement. Which that's essentially is 128 multiplied by 3, so that's 384. That's your famous number. 5 WL to the power 4 over 384 ER. That's a maximum deflection for a simple beam with a uniform load and midspan. Piece of cake, right? Is it a sin to say you love calculus? Yeah, me too, man. I really am amazed by the knowledge that people discover, you know, in calculus. It's unbelievable, isn't it? And you know, I have to say that would be the levels of calculus that knocked me out because I couldn't understand it anymore. It goes deeper and deeper and deeper. But I am still amazed by it. It's unbelievable how people can spend their hours trying to discover something about this crazy little thing. So that's it. Okay. Any questions? things will get a little rougher because you know we introduce this method to you because we need to take care of the displacement in frame. Right? So yeah, if you can get the basic concept, first you must write proper moment equation. Second, you must take care of the range of the function. That is applicable every time. Okay, so with that done, we move on to the next example, I suppose. Ooh, with that, how do you like that? With different moment of inertia. Oh. Should I do this or should I move on to the frame? How many examples do I have? Let just for a moment. Oh, oh. Oh, okay. So one more frame. So maybe a little bit about this. Okay. So what do you think is difficult? Just two eyes. So we just divide our integral by two eyes. And we need to, if let's say if there's just one load here, let's say if you don't have the uniform load, you still have to break these integrals into two parts because of the change of your section, right? But in this case, we have inconsistent loading conditions anyway. And here, I'll give you a minute or two to think about what you must do to obtain deflection and rotation at sea. So go back to the concept. If we are going to use the virtual work, we need to apply the virtual load at the location in the direction that we want to know displacement. If we want to know deflection at sea, we need to apply the unit load at sea. If we want to know rotation at sea, we need to apply unit moment at sea. Right? So say I can just write this down. First case scenario. I'm not going to draw, the beam with different eyes. Okay, you must understand that. Okay. For deflection at sea. Here. Unit moment for rotation. C. Okay. So we have this take out. We need to write moment equation, and I say now it becomes an art because you need to split your integrals here. So the first section is easy. You can just cut the free body diagram here, and again begin your x from 3m. Then be mindful of the fact that when you reach the second portion of this beam, how you want to keep your moment equation by using the reference x from C, or you want to begin again here. Think about it, right? You have a choice. And if you have watched the movie Spider-Man, when you have power, you have freedom, you have more responsibility. Now you have your freedom to choose. What do I do with this? And your choice will affect how you are going to write your moment equation for your virtual load case. Right? Now, if you So let's sit back, every time, all the time in your life, before you start doing anything, you should spend time trying to think things through. What do I need to do? What is my target? How will I get there? Folks who don't start by, spending time thinking, planning, they don't know where their destination is or how to get there. So they just, okay, I have to try to do something to get going. And here, let's say, if I use my X and then I decide to change my X here, it's okay. But when you look at your virtual load case, you see your virtual load case is very simple because you have only one load, right? You could just use one equation for the entire structure. But if you, in the actual load case, you decide to write another equation by using the reference X here, you will have to use the same reference here at your virtual load case as well. Because if you don't do it, you will have two functions with different range. You cannot multiply them together. Remember? So this comes down to basic understanding of the function. You can only multiply the two functions when they have the same domain. So if you do not take care of this, it means your integral is wrong because your fundamental knowledge of mathematics is not good enough. Okay? So what would it be if you can see this from the beginning? You would have to make a decision and then go for it. Some would prefer to, yeah, if you can see, if I cut the free body diagram here at this point and want to write my moment equation from this point on, I can eliminate this force from the equation because the moment from this point though, it becomes constant at that location. But you have the shear. So might not be a very good choice anyway. But keep that in mind. And when you start here at this point, you have constant moment because your moment diagram for the virtual load is like this. Correct? That's your moment diagram. So if you pick this point as x equal to 0, it means you begin from a constant, not 0. That's what you need to keep in mind. But if you use your x from this like all the time, you have one equation because this is one straight line. But for the bending moment diagram of this beam, it's like this, right? Straight and curve. You need two equations anyway. But it depends on, maybe you want to use x from here all the time. Writing the moment equation for this portion may be a little bit difficult, but doable. Or you want to start your x from here. But if you want to start your x again from here for this curve, you need to start your x from here for your simple load case as well, to be consistent with the domain. Or moment diagram for this should not be trouble because it's always constant. So it doesn't matter where you start, right? It's constant. So after we can take care of this, we can just start writing the equation. I don't remember what kind of format I should use. Okay, all right. Let's do this. Actual. Now I need to break this into portion. Okay, and let's say This is A, this is B, and that is C. So I have portion AB. And I should maybe try to move it. Okay. And I have my portion BC. And my portion AB, my moment equation is going to be simply minus 10x, right? Very simple. And the range is going to be from 0 to 5. And be mindful, every time you have the equation and the range, you can always substitute the number into your equation to see if it's correct or not. Because when you substitute x equal to 5, that should give you the moment at that location of beam, right? And now let's say I kind of love to stick with my origin. So if I don't change my x, I use my x from C. Right here, I still have my minus 10x as a moment, right? And then minus my W. But this time, the length of W is x minus 5. And its moment arc is x minus 5 over 2. So it's like this. Square over 2. And the range this time becomes from 5 to 10. So you see, when we plug in the x equal to 5 in this equation, the second term is gone, right? Because that's at the beginning of the uniform law. And here gives you a constant moment, again, at that point B. So here it's just about the technique to write the equation, no more. If you wish to begin from 0 at portion BC, you have a constant. Before we have a break, if for BC, x begins at B, your moment equation will become minus 50 minus 10x minus wx squared over 2, right? How do I get that? Free body diagram, force, whatever. But I don't need to write the free body diagram. Perhaps you do, because let me demonstrate. If I cut this free body diagram at B, then you have that, right? That's 10. So here is 10, and that's 50. Right? So here you have minus 50 or 50, and then you have 10, and then your x begin from there. That's why you got that. So you see, you can always, get it right with the proper free body diagram. When you have enough experience like me, you don't have to draw a free body diagram. You can just come up with the moment equation right away. But until now, if you think you're good, go on, go ahead, be cool. But when you make mistakes, coolness is completely gone, right? Because you can't be cool when you're wrong. Practice a little bit until you breathe equilibrium. You breathe free diagram, and then that's it. Practice until you are beyond your elastic limit. You never forget about it. Okay, I think we'll finish this problem before the break. Right. I think should have a break now. So, is there any question before the break? So this second break, we're gonna have 15-minute break. Okay, and back about 11:38, something like that. If you have any question, let's stop the record.